Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 2.1, Organizing Qualitative or Categorical Data. Up to this point, we've talked about how to gather the information, which is the first step of statistics. Now we're going to talk about how to organize that data and how to present it. There are multiple different types of ways of presenting and organizing data, and it depends on what kind of data we have. First, in 2.1, we're going to be talking about qualitative data, and then we'll move into quantitative data when we get to section 2.2. But first, here we have a few definitions to go through. We have a frequency distribution is a distribution that lists each category of data and the number of occurrences for each category. If you see here this example that we're going to go through in a moment, on the bottom we have this big old table here, and there's a lot of information. This is all just for different days that people would like to go and eat out. This is not really a good way of presenting data. For one, it's not organized in at least a numerical way, or at least in a time-sensitive way. So Sunday, Monday, in order like that. But also, this is just kind of daunting, and this is a relatively small data set. It only has 40 data points here. What if we had hundreds of data points? We don't want to just present each individual data point to the reader, because that gets very, very daunting. What we want to do is try to reduce this down, and that's what a frequency distribution is going to do. It's going to look at each individual data point. So for example, Thursday is the first one I see. And it's going to count how many times Thursday appears. And it's going to do the same thing for each day in the week. So it's going to do the same thing for Sunday, for Monday, for Tuesday. We're going to simply count how often that appears, and then list each category, so Thursday, Friday, all of those, with how often it occurred, i.e. its frequency. So it's a much simpler way that reduces down the fluff of presenting the data in this kind of format. You can also create what we call a relative frequency distribution. A relative frequency distribution is going to do the same thing, but it's going to very often be a little bit more important, or a little bit more relevant. What it's going to do is it's going to find the relative frequency, and that means instead of simply listing how often it occurred, it's then going to say, okay, how often did each of these categories occur relative to the overall total? So it's going to find a proportion of these. In order to do that, it's going to take the frequency for whatever category I have, and then we're going to divide by the overall total frequency. That way we find a proportion or percentage value to represent for each category. Now what we're going to do here is we're going to go through an example so you can see this being done. We have favorite day to eat out. A survey was conducted by Wakefield Research in which 40 participants were asked to disclose their favorite night to go out to dinner. Following data are based on their results. So we have these 40 data points here, these 40 categories, and this is very poorly presented. Anybody that would be reading this information would really not want this table to be given to them. Even though this is the raw data, they would want this summarized down in a way that's easier to take in. And that's what we're going to do below. You'll see that I've already filled out part of the frequency distribution. I've filled out a tally because I already went through and counted each of these. The tally section of frequency distributions are completely optional. You never really need to do a tally. This is just for counting purposes, so to help you out. But what you should always fill out is the frequency side. So this is where we have our categories listed Sunday through Saturday, and then we're going to list their frequencies. Sunday appears 3 times in that table according to my tally. Monday appears 2 times, Tuesday 5 times, Wednesday 6 times, Thursday 2 times, Friday 14 times, and Saturday shows up 8 times. This is a nice and simple way of presenting the data, showing what data point we have or what category we have, and how often did that category appear in my data. And notice with this, so far, no information has been lost. We will present something in 2.2 where we'll do a similar thing, but sometimes information can be lost in the middle. One nice way as well of checking to make sure that you did the frequency distribution correctly is by finding the total sum of these. If I do 3 plus 2 plus 5, that gives me 10, plus 6 gives me 16, plus 2 gives me 18, plus 14 gives me 32, plus 8 will give me a total sum of 40. This is exactly what we are looking for because in the description it says that a survey was conducted by Wakefield Research in which 40 participants were asked to disclose their favorite night to go out to dinner. So this agrees with the overall total that we were expecting. If I added this up and add up to 39 or 41, then that would mean that I either I undercounted or overcounted something. So it's a good way to make sure to double check that you counted things correctly because it's very easy to accidentally miss something or double count something. Now, this is all well and good. However, if I were to tell somebody that on Wednesday, 6 people said that they went to go out to eat, well, 6 is relatively arbitrary. It could be a lot, it could be just a few. 6 has more meaning when we put it relative to the overall total, which means that we're going to put 6 relative to 40. And we're going to do that with Tuesday as well. 5 relative to 40. 2 relative to 40. We're going to make fractions for each of these to represent how large or small they are relative to the overall total amount of values that we observed. And that's what we're going to do with relative frequency here. So I'm going to do 3 out of 40 and 2 out of 40. I'm going to do all of these out of 40. I'm leaving myself some room because I'm going to also divide these and find their decimal equivalent. So 5 out of 40, 6 out of 40, 2 out of 40, 14 out of 40, and 8 out of 40. This is now going to represent how big or small they are relative to the overall total. So it'll hold some more meaning. All right, if you do 3 out of 40, you will get an answer of 0.075. If you do 2 out of 40, you will get an answer of 0.05. 5 out of 40 will give you an answer of 0.125. 6 out of 40 will give you 0.15. 2 out of 40 gives you 0.05. 14 out of 40 gives you 0.35. And finally, 0.20. I did not round any of these off. However, it is very common practice to round appropriately with these. So you'll sometimes see that Sunday, for example, would be rounded to 0.08 instead of 0.075. However you do it, what you want to do then is also do another check like we did before. So we're going to sum all these up. And what we want these to all sum up to is a total sum of 1. Or if you represented these as percentages, a total sum of 100%. Note that depending how you round, it could end up being that you have an answer that's a little bit above or a little bit below 1. That does happen very, very often. Depending on how things were rounded, sometimes you'll get a sum that only goes up to 0.99 or maybe it goes up to 1.01. For example, if I did actually round these to 0.08 and 0.13, I actually would have an answer of 1.01 if I added them all correctly. That would show that a little bit of round-off error did influence the sum. But usually in those cases, it's not the worst thing to happen. That's a very common occurrence. This is one way of representing qualitative data, and it's a data-oriented way of representing it because it still has to do with a lot of numbers. What we can also do is represent this graphically using something called a bar graph, and that's what we're going to do down here. I'm going to represent a bar graph for both the frequency and relative frequencies that we created earlier. To create a bar graph, all I'm going to do is look for the frequency that I had for each of my categories, and then I'm going to draw a bar that goes up to that frequency that's represented on the left side here. So for example, Sunday had a frequency value of 3, so I'm going to draw a bar that goes up to 3, and because I like to, I'm going to shade that in. 3 doesn't show up on the frequency side itself, but 3 is somewhere between 2 and 4, so that's where I put my bar. Monday had a frequency value of 2, maybe a little higher than there. I had a frequency value of 5 for Tuesday, so between 4 and 6. 6 for Wednesday. 2 for Thursday. And the big one, Friday had 14, so all the way up to 14. And Saturday had 8. That would be a bar graph representing the data. It's usually in good practice to represent data not just numerically with the frequency table that we had above, but also graphically, because this can really help show visually what is happening between the two values. You can also do the same thing with the relative frequency bar graph that we're going to do on the side here. Now, Sunday we calculated had a relative frequency of 0.075. And 0.075 is between 0.05 and 0.1. Monday had 0.05. Tuesday had 0.125, which is between 0.1 and 0.15. Then also 0.15 for Wednesday. 0.05 for Monday. 0.35 for Friday. And 0.20 for Saturday. Now, as I shade these in, you should notice something similar about these two bar graphs. And the similar thing is that they look exactly the same. That is very, very common. What basically happened here was that the frequency numbers on the left-hand side, 0 through 16, they were all also divided by 40. 0 divided by 40 gives you 0. 2 divided by 40 gives you 0.05. 4 divided by 40 gives you 0.1. 6 divided by 40 gives you 0.15. So this relative frequency axis was a simple adjustment from the old frequency, which since it's the same values more or less, the graph itself is going to look the same. You'll sometimes even have circumstances, I'll draw a little draft of it up here, you'll have the same circumstances where sometimes you'll have a graph that shows the frequency on one of the vertical axes, and then the relative frequency that's associated with that on the other axis. So you'll have maybe 2 here, and 2 as a relative frequency corresponds to 0.05, and then 4, and then 0.1. So that way the reader can see both the frequency, so they can see, okay, how many times did it actually show up versus the relative frequency as well. You'll sometimes see that in graphs, which is a really good way of both presenting both aspects of the information. Overall, though, bar graphs are not too bad to make. One thing you do want to keep in mind, though, the way that I drew the bar graphs is kind of particular. You want to make sure that there is space between these bars. You don't want to have the bars touching each other. You'll only have bars touching each other in bar graphs if you have a multi-bar graph, where we have multiple bars representing one category. We'll have an example of that in a little bit. But when I have individual bars like this, I do not want them to touch. That will imply a different type of graph that we'll talk about in section 2.2. Another type of graph you can make for qualitative data is what we call a pie chart. Pie chart is also something that you may be familiar with, and it's just a circle like so that's divided into different sectors. Each of those sectors is going to represent one of the categories, and it's going to represent the percentage or proportion of that category, just like the relative frequency. So favorite day to eat out, we have all of our percentages here: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Although it looks like Sunday was rounded down and Tuesday was rounded up, strangely enough. So that way it adds up to 100% is what they were doing. Now, pie charts are kind of controversial in the statistical world, and you'll see more of this in 2.3. But essentially, pie charts are very, very easy to manipulate data. It's very easy to present the data that you want to in a way that it either looks larger or smaller than it actually should. And that's because pie charts are very hard to read themselves. Whereas a bar graph, we're simply trying to compare these different categories by saying how tall the bars are. When we're looking at a pie chart, what we're trying to actually analyze is how big the shapes are, so how big the area in each of the slices are. That's the difference between comparing a one-dimensional aspect, so just comparing length or height, versus comparing a two-dimensional aspect, comparing an area. The more things you add to analyze for the human brain, the more difficult it becomes, and you don't need to make it more difficult. The point is to make it easy to present and make it understandable for the reader. So you don't want to make it more complicated than it is. I will say if you do a pie chart, the way that it's presented here is very good because all the slices are on a two-dimensional pie chart. They're color-coded, which is nice, but also importantly, the percentages are given to you. So everything is presented here pretty well. Now, if we look at this, we can answer a question of, if you own a restaurant, which days would you purchase an advertisement on the local radio, and are there days you should avoid? This is a little bit of an eye of the beholder question because this can be answered a lot of different ways. Looking at this, I could see answers saying, well, put it on Friday and Saturday, because those are the two most popular days to eat out. That would be a logical time to make an advertisement. Some would instead say, well, put it on Thursday and Wednesday. If they eat out on Friday and Saturday, then you want to lead up into that. You want to give them time to consider where they're going to go eat. So if you make the advertisement on Wednesday or Thursday, they'll have time to think about that leading into the weekend. Or I've also heard some arguments saying Thursday and Monday, because Thursday and Monday are the 2 days that have the least percentage. So if you want to get more people in your restaurant and you're not seeing too much business during those times, maybe it would be good to put an advertisement on those days. There's a lot of different arguments for this, and it really depends on how you read this information, which is a very consistent theme in statistics. Or, again, is not always an exact answer. So that's bar graphs and pie charts. What we're going to do a couple examples of these so you can see some more of them. If you want, you can always pause the video and try this on your own, and then unpause and see how you did. College survey. In a national survey of 4,776 college students were asked, how often do you wear a seatbelt when riding in a car driven by somebody else? The frequencies were as follows. So we have the frequencies given here. And what we're going to do is we're going to create a relative frequency distribution, which means we're going to create this table. The table is already presented for us. We basically just need to fill in the blanks for the relative frequencies. And to find all these relative frequencies, I'm going to take each of my frequencies, so 125, 324, 552, 1257, and 2518. And what we're going to do with all of these is we're going to divide that by the total. Now, if the total is not given to you, you can always add it up and find what the total is. But in this specific case, the total is actually given to us in the description. We have 4,776 college students that were asked. So we can divide all of these by that number. Okay. So we're going to take each of these values and divide appropriately by 4,776. All right, so if I do 125 divided by 4,776, I get 0.026. What I'm going to do, I'm going to pause. I'm going to fill in the rest of these. Okay, so I have the rest of these filled in. I got 0.026, 0.068, 0.116, 0.263, 0.527. Now you may be asking why I choose to round to 3 decimal places. It's just personal preference. Unless the question says where to round, you should usually round to about 3 or 4 decimal places. That usually gives you enough information to work with. I also checked if you add all of these up, these all do happen to add up to 1. It's not a little bit off, so they do round pretty nicely. Okay, now remember that you can represent them as proportions like I do here. Proportion means this decimal. Or if I want to, I can make them into percentages. In order to make them into percentages, all I would need to do is either move the decimal place 2 places to the right, or I could also represent that by multiplying each of these numbers by 100. I can get 2.6%, 6.8%, 11.6%, 26.3%, and 52.7%. All three of these are ways of representing relative frequencies: fractions, decimals, and percentages. Unless the question asks you how to represent it in terms of a fraction, a decimal, or a percentage, you should be free to represent any of these. However, your instructor will typically give you an idea of how they want it represented. So make sure you do ask your instructor about that. Now to answer a few questions. Most of these we should be able to answer looking at our data we just calculated. What percentage of respondents answered always? Well, based on our data, we have 52.7% of respondents answered always. What percentage of respondents answered never or rarely? Well, 2.6 answered never, 6.8 answered rarely. So if I add those together, what I get is 9.4% answered either never or rarely. Suppose a representative from the center says 52.7% of college students always wear a seatbelt. Is this a descriptive statistic or an inferential statement? Well, the way that this statement is presented, it says 52.7% of college students always wear a seatbelt. Because he's trying to talk about all college students, it doesn't really make sense as a statistic, because a statistic is something that's describing a sample. What this looks like is that it's trying to jump from the data that we calculated, which we calculated 52.7%. That came from a sample of 4,776. However, this is not saying or implying that 52.7 came from a sample. This is saying just 52.7% of college students always wear a seatbelt. That sounds like they're trying to make that jump and associate this with the population. Therefore, this is an inferential statement. If you're ever trying to relate your data that you have from a sample and trying to connect or use that to represent the population, that's making an inference. If I was just trying to describe my sample, then I would say this is a descriptive statistic. For example, if I said 52.7% of the college students we surveyed always wear a seatbelt, that would simply be something describing the sample. Okay. Lastly, we have down here to create a relative frequency bar graph. So we're going to do that. For never, we had 2.6, which is a rather low percent, so something like this. Rarely was 6.8, so a little bit higher. It's kind of hard when it's scrunched up here. It's usually harder to make bar graphs when the bars are really, really different from each other, as you'll see from the percentage for never and also always. Sometimes had 0.116, so a little bit above 0.11. Most of the time was 26%, so about somewhere between 2 and 3, 0.2 and 0.3. And 52.7 for always goes above 0.5, so somewhere around there. It is a lot harder to draw the graphs when you see this bar of always is so different than it is for never. But also what this gives the reader is a way of visually seeing how stark the difference is between never and rarely, simply by looking at how tall the bar for never is and how tall the bar for always is. Nice one-dimensional comparison. Lastly, if a certain college has 12,728 students, how many would we expect to never wear a seatbelt? Well, remember, for never, we had 0.026, or 2.6%, said never. But that was for the 4,776 that we interviewed. This is asking for a completely different amount of students. Well, the way that we're going to do that is that if we found 0.026 and we trust our information, then we should kind of expect that data to also be present in other data sets. For example, this 12,000. So what we're going to do, we're going to take 12,728, and to find how many of them we would expect to never wear a seatbelt, we're going to multiply by our proportion of those we calculated to never wear a seatbelt, 0.026, and that will find how many of that 12,000 never wore, or we would expect to never wear a seatbelt. So 12,728 times 0.026 will give us roughly 331. So I will use this sign, which means approximately. So approximately 331. Now, in most classes, you won't need to use this symbol. I like to use this symbol to represent the fact that I rounded. The answer here actually comes out to 330.928 if you use 0.026. But I rounded that up to about 331. Okay, so that's it for that one. We have a couple more examples here, and then we are done for this section. I think we only have 2. Yeah, okay. Identity fraud occurs when somebody else's personal information is used to open credit card accounts, apply for a job, receive benefits, and so on. The following relative frequency bar graph represents the various types of identity theft based on a random sample conducted by the Federal Trade Commission in a recent year. So we have our bar graph presented here. What we're going to do is simply read it. Notice the bar graph, though, is a horizontal one. The bars are reaching off to the right side here instead of going up to the sky like the previous ones. That's perfectly fine. If you decide to put your categories here on the vertical axis, that means the horizontal axis is going to be your relative frequency or your frequency. Either way, they are still read the same. So we have, if there are 10 million cases of identity fraud in a recent year, how many were credit card fraud? Well, we have credit card fraud, according to this graph, we have it goes up to a little bit over 0.25, maybe I'll round to about 0.26. So we have 0.26. That's the proportion we have for identity fraud. We have 10 million cases, and we want to see how many of them we would expect to have been identity fraud. Similar to the last question, we can take our proportion and we can multiply by the total amounts of individuals we're working with, the 10 million cases. So 10, 1,000 million, 10 million cases, and we should be able to find how many of these cases we expect to have identity fraud. So if I do 0.26 times 10 million, what I get is 2,600,000. So that's about how many cases I would expect to be identity fraud out of 10 million, according to my data here. Secondly, if the Commission claimed the results indicate that 17% of all fraud committed in that year was from utilities fraud, which, looking at our graph, utilities fraud is right there, does seem to be right between 0.15 and 0.20, so the proportion or percentage they have presented looks accurate. Would you say the statement is descriptive or inferential? Well, looking back at our description, we know that this data came from a random sample that was conducted by the Federal Trade Commission. And it's saying the results indicate that 70% of all fraud committed in that year was from the utilities fraud. All fraud is trying to represent the population. Therefore, this is yet again inferential, because this is trying to make that inferential leap from a sample into a population. All right, so just another example of reading bar graphs. We have one more example, and this is something that I had alluded to earlier, what we call a side-by-side bar graph. Desirability attributes. A random sample of 2,163 adults was asked, given a choice of the following, which one would you most want to be? So they were asked, would you like to be richer, thinner, smarter, younger, or none of these? So they were given the option of which of these they would like to have been, or they would like to be if they had the choice. And this is a side-by-side bar graph, which, as you see, that means that each category, so richer, has 2 bars representing that, one blue, one green, and we see the legend in the top corner tell us which of these bars means which. The first bar is the blue one, means male, and green, the second bar, represents females. So we have what proportion of males said richer, what proportion of females said richer, what proportion of males said thinner, what proportion of females said thinner, and so on and so on. So that's what a side-by-side bar graph is. However, notice between the categories, so between richer and thinner, there is still a space. There should always be a space between your categories when you're making a bar graph. Okay, now reading this, what proportion of males would like to be richer? Well, looking at this, we have males was blue, so we look at richer, and we're looking at the blue bar. And so I'll say about 0.45. It looks to be a little bit above that, so maybe if you want to say 0.46 or 0.455, either of those answers would probably be okay. What attribute do females desire more than males? Well, females are the green bars, so we're looking at these green bars, or the second bar, in each of these categories. The only one that we have that females are higher on than males is thinner. Thinner is the only category where females desire that more than males do. So that would be my answer there. They do tie for smarter and for none of these. However, that's not what the question was looking for. We're looking for specifically where females desire it more than males. Lastly, are the desirability attributes an inferential or descriptive statistic? Well, I don't see any statements here trying to say that these are true for the population, and given my description, it says that this is from a random sample of 2,163. So this is simply just trying to describe stuff from the sample. There's no statements here trying to connect that to the overall population. So I would say that these are descriptive statistics because they are simply describing values from the sample. With that said, that's everything from 2.1, presenting how to work with qualitative data, how to present qualitative/categorical data using bar graphs or pie charts. I will also say as a last note, there is also something called a Pareto chart that you may see some projects in Math 1040 work with Pareto charts. Pareto charts are bar graphs. It's just another name for them, but they're just a special type of bar graph. A Pareto chart will organize the categories on the bottom so that the bars that you present are in decreasing order. So your bars look like this. That's the only difference between a Pareto chart and a standard bar graph. So that would be like if I looked at a previous bar graph that we worked with, for example, this identity theft, and I reorganized it so that credit card fraud was first, then utilities fraud, then bank fraud, and then it looks like other, then employment, and then government, and then loan. So I put it in decreasing order based on how tall the bars are or how large the frequencies are. That's a side note, and that's if you need to make a Pareto chart, that's all you're doing differently. It's still a bar graph with separate pieces. You do tend to see these more in business cases, and sometimes you'll also see a line chart with it that's basically showing the percentage growth over time, but that's not as relevant for our course. But hopefully with that, you should be able to answer everything from the homework for section 2.1, so I recommend giving that a shot before moving on into section 2.2. But with that said, I hope you have a great day.